This is example 1 for chapter 18, which deals with the ideal gas law. And the ideal gas law states that the pressure times the volume is the number of moles times the gas constant times the temperature. There's also a version of it where it's the number of molecules times the Boltzmann's constant times the temperature, and we'll deal with both of these equations as we need to. So for the first example, we're given that we have an initial pressure, initial volume, and an initial temperature. And then after some time, this leads to some final pressure, some final volume, and some final temperature. And if we notice that the NR, since both of those are constant, if we solve for NR from either equation, we're going to get the relationship that the pressure times the volume over the temperature has to be the same whether it's the initial condition or the final condition. We're assuming V final equals V initial because there's no volume change. So now we can say that P final over P initial equals T final over T initial, which means that P final is going to equal T final over T initial times P initial. And now we have all of these values, so we can plug in. One thing to note here is that the temperature has to be in Kelvin, so 35 degrees Celsius plus the 273.5 to change it to Kelvin. That's T final, and T initial was 18 plus the 273.15, and then times the initial pressure, which is 7 times 10 to the 5th Pascal. And if we do this, we find out that it's 7.41 times 10 to the 5th Pascals. Now you might ask, well, what if it's not ideal? If we have a gas that's not an ideal gas, I should have said not an ideal gas, then we have something called the van der Waals equation, which is the pressure plus some constant A N over V squared times V minus NB equals nRT. And if you notice, if A and B are 0, then we get exactly the ideal gas law. So the ideal gas law is nothing more than a special case of the van der Waals law.